This video lesson covers global warming in the form of a class debate. Rebecca Bennett is the original creator of this lesson plan, and modifications were made by Derek Spencer. This video lesson was made possible through the NSF-funded Boat of Knowledge in the Science Classroom project at Ohio University. Global warming can be defined as the gradual increase in the average global temperature of the Earth. It is generally attributed to elevated carbon dioxide as well as other greenhouse gases within the atmosphere. While not synonymous with climate change, these two terms are often used interchangeably to describe the same phenomenon. To be a little bit more specific, the term climate change is used to describe any shift in climate over relatively long periods of time. Climate should not, however, be confused with weather. Climate is an established pattern of atmospheric conditions which include temperature, humidity, precipitation, pressure, wind, and other factors. Weather is the day-to-day measurement of these variables. In essence, climate is a depiction of the average weather over a long period of time. Before delving too much further into Earth's climate, let's discuss global warming as a class. Do you believe global warming is an issue to be worried about? Is the climate changing in response to human activity, or are we currently experiencing a natural fluctuation in climate? Or perhaps is it neither? Pause the video here and split into several groups for a discussion on climate change and global warming. Ideally, one side should argue for man-made climate change and the other against man-made climate change, but all opinions may be entertained. Keep an open mind, and while discussing, make sure to respect others' opinions. You may have heard of the habitable zone of our solar system, which outlines the distance away from the sun where life is most likely to flourish and water able to exist in liquid form. But how is the temperature of a planet influenced aside from its distance away from the sun? We need only look at the inner planets of our solar system closest to Earth for answers. Venus is often referred to as a sister planet of Earth. The two planets are roughly the same size, but the surface of Venus happens to be 420 degrees Celsius on average, while the Earth is roughly 15 degrees. Mars, on the other hand, is much colder, with an average surface temperature of minus 50 degrees Celsius. Obviously, the temperatures on Venus and Mars are not suitable for human life. If Earth's atmosphere was thinner or non-existent, it might be a cold planet like Mars. On Mars, not enough thermal energy is absorbed by the atmosphere, and a lot of it is reflected back into space. With a thicker atmosphere, Earth might be unbearably hot like Venus. On Venus, a lot of energy is absorbed and retained by the atmosphere. Of course, there are many variables involved with how hot or cold a planet is, including distance from the sun, axis and speed of rotation, and the presence of a molten core, but the density and composition of the atmosphere plays a vital role in temperature regulation that cannot be overlooked. For the remainder of this video, we will look at how the Earth's climate works and how it may be influenced by external forces. In order to understand how our climate works, we can think of the Earth's atmosphere, along with its surface water, as a large heat engine. Energy from the sun is received nearest to the equator and is absorbed by the surface of the Earth. This energy is then spread across the surface of the Earth via evaporation of surface water, wind, rainfall, and ocean currents to reach a thermal equilibrium. In fact, wind is actually generated by the difference in density between hot and cold parcels of air. Hot air rises and displaces cold air, generating what we perceive as wind in the process. These energy redistribution processes are largely temperature-driven, meaning differences in temperature from one area to another results in the physical movement of gases and liquids. So, if Earth were a car, the thermal energy from the sun would be the fuel, and the movement of water and atmospheric gases would be the kinetic energy generated from the use of that fuel. Our climate is driven by energy supplied by the sun, and differences in topography, as well as proximity to water sources in the equator, determines local climate. Earth's temperature is regulated in a complicated surface-atmosphere interaction. Most of the energy received by the Earth from the sun is in the form of near-infrared, visible, and near-ultraviolet electromagnetic radiation. The Earth reflects energy back into space in the form of infrared radiation, with some of that radiation retained by greenhouse gases and reflected back to the surface of the Earth. This interchange of infrared radiation between the surface of the Earth and greenhouse gases in the atmosphere is like a never-ending game of Pong. Earth's atmosphere, therefore, acts as a sort of blanket which helps retain heat energy received from the sun. This figure helps to visualize the flow of electromagnetic energy from the sun to the Earth. First, solar radiation in the form of ultraviolet, visible, and infrared light reaches the outermost layer of the Earth's atmosphere. Of this radiation, the ultraviolet light is mostly absorbed by the ozone layer within the stratosphere, shielding organisms from damaging high-energy ultraviolet rays. Part of the incoming visible solar radiation is also reflected back into space by cloud cover. This has a cooling effect on the Earth because this radiation never actually reaches the Earth. The surface of the Earth absorbs about 50% of the solar radiation which penetrates the troposphere, having a heating effect. Some of the excess infrared radiation is absorbed by gases in the troposphere, which warms the Earth as well, and some of the infrared radiation escapes from the Earth and cools it down, thus balancing the solar radiation absorbed by the Earth's surface. After all is said and done, the net energy flowing into the surface of the Earth is equal to that flowing out. A balanced energy budget needs to meet this criteria, and the temperature of the Earth will adjust to fulfill this requirement. All solar energy which reaches the surface of the Earth is radiated in the form of long-wave infrared radiation. This figure gives a more detailed view of the thermal energy inputs and outputs associated with solar radiation. Flows in yellow depict the fate of incoming solar radiation, and flows in red depict outgoing surface radiation. In a balanced energy budget, incoming energy is equal to outgoing energy, and no heating or cooling occurs. In an unbalanced budget, more energy is being absorbed by the surface than is reflected. In the case of an unbalanced budget, the temperature of the Earth would change to reach a radiative equilibrium. The most important takeaway from this figure is that outgoing radiation is equal to incoming radiation. Global warming will not occur unless back radiation from greenhouse gases increases, increasing the amount of radiation absorbed by the surface, and thereby increasing the temperature of the Earth. As stated here, a greenhouse gas is any gaseous compound in the atmosphere that is capable of absorbing infrared radiation, thereby trapping and holding heat in the atmosphere. By increasing the heat in the atmosphere, greenhouse gases are responsible for the greenhouse effect, which ultimately leads to global warming. Here we will go over some of the most prevalent greenhouse gases present in our environment. Not surprisingly, water vapor is the most predominant greenhouse gas in our atmosphere, contributing from 36 to 72% of the overall greenhouse effect. Because the concentration of water in the atmosphere is dependent on temperature, its effect varies from day to day. Water vapor is not as much of a concern as other greenhouse gases, because its presence is guaranteed in the atmosphere regardless of human activity. However, the role of water vapor in climate is absolutely vital, and cloud formation is known to significantly reduce the greenhouse effect by reflecting part of the incoming solar radiation back into space. Carbon dioxide is the second most prevalent and most notorious greenhouse gas, contributing 9 to 26% of the greenhouse effect. CO2 is a stable end product of cellular respiration and combustion reactions, and most organic carbon-containing gases are eventually oxidized to CO2. It is removed from the atmosphere via photosynthesis and ocean adsorption. Methane is an end product of microbial metabolism, especially in landfills and ruminant mammals. Power plants, rice agriculture, and wetlands are also significant sources. Methane contributes about 4 to 9% to the greenhouse effect and has 25 times the greenhouse effect potential as CO2. So, a release of 1 kilogram of methane has the same effect on warming of the Earth as 25 kilograms of CO2. Ozone is another important gas in the atmosphere and plays a positive or negative role in climate depending on its location within the atmosphere. Stratospheric ozone is considered as good ozone, and tropospheric ozone is considered as bad ozone. Ozone in the stratosphere is considered as the sunscreen of the Earth because it is able to absorb nearly 97 to 99% of all incoming solar ultraviolet radiation before it enters the troposphere. Ozone in the troposphere, however, is highly reactive and is a precursor to photochemical smog. Low-level ozone also absorbs infrared radiation and contributes around 3 to 7% to the greenhouse effect. Other greenhouse gases exist. Actually, quite a lot of trace gases could be classified as greenhouse gases, but they are not present in high enough quantities to make a contributable effect to warming. Now that we understand a little bit more about our climate and greenhouse gases, are humans actually contributing a significant amount to global warming and climate change? Or is the Earth undergoing a natural warming cycle? At this point, we will conduct a research team debate on global warming, split into 3 groups of equal students. Each group will research one of the 3 positions listed above. First, that global warming is being exacerbated by human activities. Second, that global warming is occurring but is not caused by human activities. And third, that we are currently not experiencing global warming. Use the internet to compile your information and cite your sources. The debate will begin with all slides presenting their initial case in PowerPoint format, then as a point-counterpoint format to argue your case. If there are no or few proponents for any group, part of the class will be assigned to play devil's advocate. Alternatively, if a group has a different position they want to take, they may do so if they can create a strong enough case for it. Bonus points may be awarded to the group which decides to play devil's advocate.